All right, let's jump right into this guide to one of the most important topics in A-level physics, materials. We're going to break down all the key concepts and maybe more importantly, all the equations you're going to need to really master this stuff.
So here's our game plan. We'll kick things off with the absolute basics, like density. Then we'll see what happens when you put objects in fluids. After that, we're going to pivot to solids, get into how they stretch and what that tells us about them. And finally, we'll look at where all the energy goes when you deform a material.
Okay, first things first. Let's talk about the most fundamental property of pretty much any material you can think of. It's density. So density, we use the Greek letter rho for it. And it's really just a measure of how much stuff is crammed into a certain amount of space. Think about a kilogram of feathers versus a kilogram of lead. Same mass, right? But the volumes are wildly different, which means they have very different densities. The equation couldn't be simpler. It's just mass divided by volume. Let's lock this one in. It's our first key formula.
Okay, so we've got density down. Now let's see how that concept actually plays out when we put materials in a fluid. Something like water or even air. This is where two really important forces come into play.
Have you ever just looked at a massive steel ship and wondered, how on earth does that float? Well, the secret is a force called upthrust. It's this upward push from the fluid that fights against the object's weight. And thanks to a genius named Archimedes, we know that this upward force is exactly equal to the weight of the fluid that the object pushes out of the way.
And of course, there's an equation for that. The upthrust, which we call U, is equal to the density of the fluid, that's rho, times the volume of the displaced fluid, that's V, all multiplied by G, the good old gravitational field strength. It's basically just the weight of the water that got moved. Now, this is a really classic way to solve these kinds of problems. For anything to float, the forces have to be balanced. Simple as that. So its downward weight, W, has to be perfectly canceled out by that upward push, the upthrust, U. By setting those two equations equal to each other, mg and rho vg, we can solve for all sorts of useful things, like exactly how deep that cube is sitting in the water.
So that's floating. But what if an object isn't just sitting there, but it's actually moving through the fluid? Well, then it has to deal with a different force called viscous drag. The best way to think of it is as fluid friction. You know that feeling when you try to run in a swimming pool? Yep, that's viscous drag in action. Now we have this fantastic equation for calculating drag called Stokes' law. But, and this is a big but, it comes with some very strict rules. It only works if the object is small, perfectly spherical, and moving pretty slowly. Why? Because if any of those things aren't true, the fluid flow around it gets all chaotic, and this simple, elegant law just doesn't work anymore.
And that all comes down to the type of flow. On one hand, you have laminar flow. Imagine a river flowing super gently, all the water particles moving in nice, smooth, parallel layers. On the other hand, you have turbulent flow. That's the same river hitting a bunch of rocks and turning into a chaotic mess of whirlpools and currents. Stokes' law? It only applies in that calm, predictable, laminar world.
So here is the equation itself. The drag force, F, depends on a few key things. First is eta. That's the fluid's viscosity, basically how thick it is. Think honey versus water. Then you've got R, the radius of our sphere, and V, its velocity. It makes sense, right? The faster you go or the thicker the fluid, the bigger that drag force is going to be.
All right, we're going to pivot now. Let's shift our focus away from how fluids push on objects and start looking at how solid objects themselves behave when you pull on them. And this brings us to one of the most foundational principles in all of material science, Hooke's law.
Hooke's law is this really elegant, simple rule that applies to things like springs and wires. It just says that, up to a certain point, the amount it stretches is directly proportional to the force you apply. Double the force, you get double the stretch. In the equation, K is what we call the spring constant. A really big K means you have a super stiff spring, like in a car's suspension. A tiny K means you have a loosey-goosey spring, like the one in a ballpoint pen. So Hooke's law is great for one specific spring, right? But what if we want to talk about the inherent property of, say, steel itself, not just one steel wire? To do that, we need to move beyond just force and extension. And this is where the concepts of stress and strain come into the picture.
First up, we have stress, and we use the Greek letter sigma for it. Think about it like this. If you walk on fresh snow in your boots, you're going to sink, right? But if you wear snowshoes, you stay on top. The force, your weight, is exactly the same. But because the snowshoes have a much larger area, the stress is way lower. It's just force per unit area.
And the partner to stress
is strain, or epsilon. Instead of looking at the raw extension, like how many centimeters it stretched, strain is a ratio. It's the change in length divided by the original length. This gives us a really nice proportional way to measure stretch. A 1-meter wire stretching by 1 centimeter has the exact same strain as a 10-meter wire stretching by 10 centimeters. And the cool thing is, because it's a length divided by a length, strain actually has no units.
Now here's where it gets really powerful. If we put those two ideas together, stress and strain, we get something called the Young modulus. This is a fundamental property of a material. It's the ultimate measure of stiffness. It tells us how much stress you need to apply to get a certain amount of strain. A material like steel, for instance, has an incredibly high Young modulus. You need a massive amount of stress to get even a tiny bit of strain.
So how does all this look in the real world? Well, we can actually plot a graph of stress against strain, and what we get is amazing. It tells the entire life story of a material as it gets stretched, right up until the very moment it breaks.
Every one of these graphs has a few key landmarks you need to know. First, you've got this nice straight line part at the beginning. That ends at point P, the limit of proportionality. In this zone, Hooke's law is being obeyed perfectly. If we push a little bit further, we hit point E, the elastic limit. Go past this point and the material will not go back to its original shape. It is now permanently stretched. Keep pulling, and eventually you hit the breaking stress. And snap! It's all over.
So that graph really shows us the two main ways a material can deform. Elastic deformation is like a rubber band. You stretch it, you let go, it snaps right back. No permanent change. But plastic deformation is like bending a paper clip. Once you go past that elastic limit, it stays bent. Forever.
That brings us to our last big topic, energy. I mean, when we apply a force to stretch a material, we are doing work on it, right? So, where does all that energy actually go? Well, as long as we're in that elastic region, the work we do is stored inside the material as elastic strain energy. The equation for it is 1/2 times the force times the extension. And here's a neat trick. If you have a force extension graph, the stored energy is simply the area underneath the line.
And here they are, all in one place. This is basically your toolkit for this entire topic. From the simple idea of density all the way to the energy stored in a stretched wire, these are the equations that let us describe, predict, and engineer the behavior of pretty much any material. So, you see, these principles are not just abstract equations on a page. They're the design rules for everything in the world around us. Think about that bungee cord. You'd want a material with a really low Young modulus, right? Something super stretchy that can store a massive amount of strain energy without snapping. See? The physics defines the function. So what other material properties do you think would make the perfect bungee cord?